This video is going to talk about finding the asymptotes, the vertical and horizontal asymptotes for a rational function of equal degrees on the top and bottom. So for example, right here you have 3x squared, and down here you have x squared, so they're equal degrees. And when we go ahead and find the asymptotes, the first thing we want to do is factoring. I've done all the math here through this problem because the video will able to be a reasonable length if I could just point out the math that I did as opposed to trying to do all those calculations during the video. But the main thing for asymptotes is just going to get focused in the factoring, okay? And so we aren't going to worry about a lot of the things that I have here. We'll do that on a later video when we actually try to graph this function completely. And the asymptotes are kind of like guardrails where the function runs along. And so we're just going to set those asymptotes or guardrails up on this video, and then we'll fill in the function itself, like I said, on a later one. Okay, so if you went and took this function, this is a trinomial whose lead coefficient is not 1. I would go ahead, as far as factoring goes, I factored it by grouping, by using the AC method. I came up with two numbers that multiplied to -6 and added to -5, and they would be -6 and 1. And I was able to go ahead and use grouping to factor this, and you could go ahead and go through this math yourself if you want to see exactly what I did. But by the time I was done, I had the factors of the numerator to be x minus 2 and 3x plus 1. And on the bottom, it was the difference of two squares, and there I factored it into the product of the sum and difference of their square roots, x minus 3 and x plus 3. Okay, so I'm going to go ahead and take a look at the vertical asymptotes first. The vertical asymptotes come from the factors of the denominator. It turns out on this particular function, the denominator has the factors of x minus 3 and x plus 3. Well, we can't actually have the value of 3 or -3 in this function. They're limited from the domain, and you can see that right here. And the reason being is if you did put a 3 in here, you'd be dividing by 0, because 3 minus 3 would be 0. The denominator overall would be 0. And likewise, -3 would make this factor 0, and the denominator would be 0. So you can't actually have, and you see I put it in set builder notation, the domain could be the set of all x such that x can be any real number but not 3 or -3. But what happens when you get really close to those values is you get extremely small numbers in the denominator. For example, imagine, and right down here is what I'm going to do, is I'm going to go ahead and come up with the behavior near the asymptotes when we go to graph by using numbers really close to there. But because this video, for example, 2.99 minus 3 is really close to 3, but it produces a really small number. But we'll worry about that more when we actually try to do the graph. Let's just put in the asymptotes themselves. So there will be a vertical asymptote at 3 and at -3. So I'm just going to go ahead and draw those dotted lines. They're not part of the functions graph. They're going to be, like I said earlier, the guardrails that the function will run along. So I'll just go ahead and put a vertical line, an imaginary line. That's why I'm dotting it, because it is not the function itself. It is a line that the function will grow near for certain values. And I'm going to do the same thing here at -3. Okay, so they're the vertical asymptotes of the function, and what we'll see later when we do graph it is that, you know, the function may come up this way, or it may come down here or up here. And the reason why the values get really big as you get close to those asymptotes is because, like I said, if you put in numbers really close, like -3.01, you're going to go ahead and end up with a situation where you're going to get a really small value in the denominator, and dividing by that small value will give you a really big value, like up like this, or a really big negative value down like that. Okay, so now let's go ahead and find the horizontal asymptotes. And what's unique about a function that is of equal degree, when you find the horizontal asymptote, all you have to do is divide by the coefficients of the squared terms here, the highest degree terms. And because they're equal, they'll always be the same power here. And 3 over 1 is going to be an equation that is a horizontal line. It's 3, and the horizontal asymptote will be 3 over 1. So when you have an equal degree, all you have to do is divide the coefficients of the elite coefficients of both the numerator and denominator, 3 over 1, and that will produce your horizontal line that your graph will eventually approach as you go out for big values of x, whether you go out far this way or out far that way. So I'm going to draw another dotted line, but this time a horizontal one that represents y is equal to 3. And the reason why it starts to behave like that is because if you put in really big values in here, like 100, let's say, and 100 down here, these amounts really won't make much difference compared to the fact that you got 3 times 100 squared over 1 times 100 squared, which is basically 3 over 1 when you do that division. So it starts to act like a horizontal line at 3 for when you get out here far enough. Okay, but that's it. There are both our horizontal and vertical asymptotes. Vertical asymptotes you find by the factors of the denominator, and horizontal asymptotes are unique to a kind of rational function you have. When you have an equal degree, like this video is covering, then you're dividing 3 over 1, and that should be a horizontal line at 3.